Okay, I'm gonna give you a little challenge. I have a set of 3 graphs here, and you can see the first one. This is a position versus time graph. The second one is a velocity versus time graph, and the third one is an acceleration versus time graph. And these are all from Moving Man that I did with him. So I'm gonna show the movie in a second, but look at the graphs, pause the video, and see if you can predict what his motion is based on what's given by these 3 graphs. And we'll look at it in a second. All right, so I'm gonna start the Movie Man movie here, and I'll pause it at different points for us to talk about what's happening. So let's start it. Okay, so you should have noticed the position time graph for Moving Man is at 0 here. This is the position time graph. So you should have realized that he's standing still for the first, say, 4 seconds. Notice he also has a 0 velocity. He also has a 0 acceleration, right? So the first 4 seconds, standing still. Then as it continues, we see a curved line on the position time graph, which tells us that he has an acceleration. So starting at 4 seconds, he had a positive acceleration, which meant his velocity was increasing in a positive manner, in the positive direction. And we can see this increase in velocity here as his velocity went from 0 to 2.4 and then continued to increase. Okay? So right now, Moving Man is at the edge of the screen, and you can see that he is now standing still. Here he is. His velocity has gone back down to 0. His acceleration is 0. The next part of the graph we see this acceleration. Now, the slope of this line is a negative slope. So that tells us his velocity is negative. And we see here that it's going to be a negative velocity because the velocity time graph is in the negative region, which tells us he's going to be walking back in this direction. Okay, so right here at 10 seconds, we see Moving Man begins to walk in the negative direction. He's walking with an increasing speed. We see him moving faster and faster and faster. So that's why his velocity is increasing. And now he has a constant positive acceleration. We see his velocity is positive. We see his velocity is slowly gaining. It's becoming more and more positive. So he is now off to the edge of the screen somewhere over here, heading back this way. So, and there you go. You see him. Here he comes. There he is, Moving Man. So there's a lot going on in these videos, but this position, velocity, and acceleration graphs are a simple way to understand what his motion or what the motion of any object would look like. So let's talk about a situation of an object falling. A falling object is undergoing a constant acceleration, and the acceleration is due to gravity, right? Gravity brings everything down to the center of Earth or towards the ground. So a ball that's falling is undergoing constant acceleration, and what we see with its displacement is that each second, so this picture shows each second of the ball as it falls. What we should see, and what we do see, is that each second, the distance the ball falls becomes greater and greater and greater. And the reason that is because the ball's speed is increasing. So as the ball's speed increases, the distance it falls increases for each second. This is an interesting video from MIT. This is their physics department showing the same thing, but this is live action. So you can see that same motion under constant acceleration. The distance traveled each second is increasing. So enjoy. So we see these are at equal distance apart from each other. Awesome. Now watch in slow motion here. And what we can see in this final image is the exact same thing. Under constant acceleration, the ball falls a greater distance each second, which is kind of cool. All right, so the last part of this video, I want to introduce an equation that you can use when solving problems with constant acceleration. All right, so this is a graph, velocity time graph. So it's a velocity on the y-axis, right? So that's our dependent variable, and time on the x-axis of an object moving with constant acceleration. And we know it's constant acceleration because the velocity is steadily increasing. The slope of a velocity time graph is the acceleration of an object. So this is an important point. The slope of a velocity time graph is the acceleration. Okay, and then we see the positive slope will give us a positive slope for this line. Tells us the acceleration is positive, and negative slope tells us it's a negative acceleration. Okay, so just to kind of look at this, if the slope of a velocity time graph is positive, as this is, it tells us it has a positive acceleration, which means its velocity is getting more and more positive. If the slope were negative, say in this direction, right, we'd say negative slope, we would say the object would have a negative acceleration. So looking at this graph, we see that the object starts at zero, both zero velocity and at 0 seconds, and continues to increase its speed, at which point at 1 second it's at 120. And so if we can find the average velocity of a constant acceleration situation by finding the halfway point. So the average velocity isn't 120 or 0, it's 60, which is right in between. So that leads to a new equation. And the equation looks like this. If you remember that delta, let's do that. Yeah, we'll do it around. Delta x over delta t is equal to the average velocity for an object, which is equal to vi plus vf divided by 2. So in other words, this means if you start at 0, you accelerate up to 100, say miles per hour, your average velocity is 50. 0 plus 100 divided by 2. Okay? What we can then do is we know that velocity, since these two are equal, since they both equal the average velocity, we can set them equal to each other. So we end up with a situation like this. Delta x over delta t equals vi plus vf over 2, which if we rearrange this, we now can have a new equation, and the new equation looks like this. It's the displacement of an object is equal, is equal to 1/2 vi plus vf times delta t. So this now is a new equation for our tool belt that we can use to apply to physics problems at constant acceleration. All right, I hope that makes sense. If you have any questions, ask in class. And always remember, physics is fun.